What's going on, guys? This is Dustin Stelzer with another episode of Electrician U, and today we're going to talk breakers and how breakers actually work. Alright, so today we've got two sub panels, and in these sub panels are a bunch of breakers. These are the two sub panels. Sorry, I can't keep the damn doors open. The wind's blowing down here. But you get the idea. So each one of these sub panels has a main breaker. We call it a main. And then it has a whole bunch of other branch circuit breakers. So this panel is pretty much all 220 volts. We don't have any 110 stuff in here. This is going to be furnaces, air conditioners, water heater, washer and dryer stove, stuff like that. And then this one, we have only non-arc fault loads. So I don't like to put arc fault stuff outside, especially like being down here by the ocean. Things corrode and anything with electronics in it. I just try not to keep any of that stuff outside. A good old boy electrician taught me that one. It's actually a really good idea. So anything that's non-arc fault, any exterior weatherproof circuits, any appliances, or anything that fits in the house that's not supposed to be on arc fault in code is out in this panel. So let's look at this for a second. Somebody asked me a question recently on YouTube, and they said, how do breakers actually work? Like, do breakers put power out? You know, does this like 60 amp breaker push 60 amps of electricity out? And the answer is no. So the way that you have to think about electrical systems is that you have a difference of potential between these two hots. If I were to connect these two hots right now, so much electricity, so many electrons would run through those two wires, and they go straight out to the utility. There's a little transformer out there. But so many amps would fly through those circuits, or through those wires at a given time, that they would fucking explode. Like, it'd be a massive amount of energy that would be released. Power always travels from the source at the utility all the way to the house and then back out to the source. So what we do is, when we add all of these other wires, we're bringing wires out to specific loads. And loads, the very nature of a load is that it slows electricity down. There's resistance in it, or there's inductance, or there's capacitance. There's something in that circuit that slows the electricity down. So essentially all we're doing in a panel is we're connecting this wire to that wire. But instead of directly connecting them, we're connecting them through equipment. That equipment has enough resistance in it, or has motors and has windings of wire, that it slows electricity way, way, way down. So we put breakers in here. Breakers are just little switches, essentially. Like, you turn this on and turn it off. It's just like a normal switch that you would have on a wall. But the cool thing about the breakers is that breakers can sense a certain amount of current going through them. Inside of them, they have an electromagnet. And the bigger breakers, like a 60, or like this one's a 125, these bigger breakers, the magnets inside of them are a lot stronger. So a certain amount of amperage running through an electromagnet is going to suck that electromagnet away, or it's going to close it. It's going to do something, you know, open or close the circuit. So breakers are really just ways to stop the current flow from these conductors all the way through these bus tabs. So right now, you know, like, we would have power going through here. This is 40 amps. Let's just say that this is an air conditioner. So current is going through here all the way to the air conditioner. That air conditioner is going to be spinning and turned on. So power is traveling very, very slowly through this circuit. But for some reason, if in that air conditioner there's a short, well, that short's going to make a whole shitload of current go fly through the circuit, just like it would if we connected these two wires. So if that were to happen, we would have like an explosive amount of energy. It would catch things on fire. It would, you know, melt the equipment. So we put a breaker in that's rated at a certain amperage so that it can handle a short. When a short happens, this thing just trips in the off position. because it's a 40 amp, it can handle up to 40 amps before it automatically trips and disconnects. So breakers don't put out any power. How power happens is by connecting this line to this line, or this line to this line. But again, if we just like directly connect those wires, it's gonna fucking blow up. So we have to put a load in between those wires of some sort to be able to slow the current down and make it useful. So that's all we're doing with a house, is we're putting a whole bunch of wires everywhere that have specific loads on them, and that slows the current flow down. And if something were to happen, we need to have a device in here of some sort that can cut power off in case of an emergency. If something shorts out, or say a piece of equipment burns up but it keeps running, it's going to draw a lot of amperage. And so we need something that can automatically, without us being around, detect like, hey, there's a fucking problem, boom, and it just shuts the circuit off. So that's it. Breakers are just safety devices that kill power when there's a problem. They don't put any power out. They just allow power to go through them until there's a problem. And when there's a problem, boom, they disconnect. So that's how breakers work. Or that's why we have breakers. I have another video if you guys are interested on what's actually inside of a breaker. I would check that out if you're at all interested. But hope you guys enjoyed it. Leave some comments below, subscribe if you like this stuff, and I will see you in the next episode.